effectively, we are done with momentum right now. But I want to share this video with you. You may have seen it, but I want you to think about this thing. Okay? This is called the bullet block experiment. It's a very well-known video. Check it out.
All right, here is the setup. I have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. So obviously the block is going to go flying into the air. But we're going to do this again, and instead of firing the bullet right into the middle of the block, we're going to shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher?
Okay, so versus being shot in the middle when you shoot on the side is the question, right?
Yeah, how high will it go in comparison?
It depends on if the bullet stays in the block. And I'm assuming it does.
It does stay in the block.
It does stay in the block.
I guarantee you that.
Same height.
I'm purely basing it on just like an instinct that I have.
I feel like I'm being tricked.
I just feel like you're trying to trick us and that it's going to do something that we can't predict.
I thought the obvious answer is not as high, so I'm going to say higher.
I'll say higher. But it's going to like fly in a direction or something. So you have angular momentum, which is L, and you have translational momentum, which is P.
Yeah.
When you hit it in the middle of the block doesn't really spin at all, so it just goes up a certain height. But when you hit it on the side of the block, it's going to be spinning, so it's going to have imparted some kinetic energy, so there won't be as much potential energy.
And so the total energy of the system
basically has to stay constant, and the kinetic plus potential, which would be the height it goes to, will have to be constant. So if it's spinning and has kinetic energy, it can't go as high. That's my prediction.
So my prediction is it'll go up, not as high, but it'll spin more if it's hit to the side. Am I wrong?
I want you to think, which do you think is the most reasonable, and then click one of the annotations above. All right, are you ready? Make your prediction in 3, 2, 1.
Let's go analyze this thing. Okay? Let's go analyze this thing. Let's look at this putty example here. If I look at this putty example, what is conserved and what is not conserved in this case? And the answer is that if I think about the bullets example, here we're talking about putty, how it being much, much bigger than the force of gravity. Now think about a bullet hitting a block. What would the forces look like? You would have to conclude that the force of the collision must be much, much greater than the force of gravity. So if we come back here to this here, so if we come back to the bullet block experiment, we have to conclude that if the force of collision, that means the bullet with the block, is much, 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 much greater than the force of gravity, then the total momentum before must be equal to the total momentum afterwards. What is another way of saying momentum is conserved? What did we start talking about at the beginning of this chapter? What's another thing that's conserved? It has to be V center of mass. Or I could say V center of mass before must equal V center of mass afterwards. So if you had to respond to this video here, what would you respond as? Right? Will the spinning block go higher, the same height, or not as high? What would you predict now that we've sort of like talked about this thing? Let's see if we could find this video. Right? So where is the second video? The second video is, where is this? We don't want the explanation. We just want the video. Oh, here it is. Okay. So let's go watch it.
This pandemic has taught us something.
So I'm going to go share my screen with you. And of course, there's some.
It's that we're stronger together.
Our community is so capable of.
All right, let's watch it.
Okay, here we go.
Derek's giggling to himself right now.
Okay, you have made your prediction. Now it's time to find out which block went higher. The one that's shot off center or the one that's shot right into the center of mass. Okay, we're just getting set for shooting straight into the block. How are you feeling about this one, Dave? I think this is the one. I really do.
Okay, range is going hot. And 3, 2, 1.
We've moved this block, so now the gun is actually firing into the right side of the block. So presumably, one imagines that the block will spin anti-clockwise.
3, 2, 1.
Now check out the high-speed footage. You can clearly see that both blocks go to the exact same height, even though one is rotating. And that's a bit strange because they were both hit by the same type of bullet from the same rifle, so presumably it had the same kinetic energy. And they both go the same height, so they both have the same gravitational potential energy, but one is rotating.
Wait.
Additional rotational energy.
I got to pause that. Now, did that surprise you? Let's go analyze this thing. So let's go look at this thing. Here, let me go back to my window. What you're seeing here is that when I look at the system here, we know that the bullet block collision is internal. Therefore, V center of mass before must equal to V center of mass afterwards. And what did I keep saying? I kept saying here that the system must readjust itself to conserve velocity center of mass. So I don't care if I have a block collision that looks like this, right? So let's say that I have a block like this, and then I have a second block. And then I have this scenario here. Right, so if I have a bullet coming in like this, oops, wrong. Let's say that this is my bullet coming in here. Or I have another bullet coming in at the side.
Hey, Carlos, we can't see your screen.
God damn it. Sorry about that. I thought I had my screen up. Are you seeing my screen now?
Yeah, we are.
Okay, right. So this bullet is coming into the center right here. This bullet is coming off to the side right here. And what you're seeing here, look at my system now. What do we know about the system? Those forces are internal. So what we're seeing here is that the center of mass, so from the center of mass picture, you're seeing the center of mass go like this beforehand, right? Of course. And then after the collision, what happens here? Well, look at the blocks. After the collision, what do we have? And remember that guy from Minute Physics, by the way, if you guys ever get a chance, watch Minute Physics. That dude's a badass. He has some incredible videos. So then check this thing out. Look at the bullet. That means that the velocity of center of mass must be with the system because they're not separated anymore. And then after the collision, even though this block is spinning, it doesn't matter because it's an internal thing. So even though the block may be spinning like this, right, where it's rotating like that, I don't give a goddamn. The fact is that the center of mass is still with the system. So what should happen? They both have the same V center of mass, which implies that they go to the same height. It's just conservation of momentum. Energy is not conserved. Why is it not conserved? Because we already said if I have a collision, in this case here, it didn't go all the way through, it got stuck, but it's still heating up. So that is not going to conserve energy, but it does conserve energy, momentum, because it's an internal force. That's why conservation of momentum a lot of the times is way more powerful than conservation of energy for that reason right there. That is an incredible video.